Hello everybody and welcome to another video about math. In this video I will be breaking down compound interest and two different formulas that make up compound interest. As you can see, we will start out with what a nominal rate is, as it's a little bit different from an annual rate. Then I'll hop over into the compound interest formula and how to find A, P, and T using the compound interest formula. Then I'll hop over into the continuous compound formula where I will find A, P, T, and R. And then lastly, we will talk about annual percentage rate versus annual percentage yield. Let's get it. Nominal rates. Annual interest rates are only good for simple interest and compound interest, in each case only if interest is being paid once per year. Anytime you get or pay interest multiple times per year, the interest rate becomes a nominal rate. So in the example here, the credit card rate is 20%, and interest on your credit card is charged monthly. So this is an annual rate. All rates are listed as annual rates, but the fact that the interest is charged monthly makes it nominal. So what I want to do now, using this example, is just figure out how can we know how much interest the credit card company is charging per month. Charging 20% per month doesn't make any sense. First of all, because this is an annual rate and we're being charged interest monthly. Those two units do not match up. So how can we figure out what the monthly interest rate is? Well, it's very similar to how we figured out how many years 27 weeks is, or whatever number you want to pick. We would have to take the interest rate and divide it by the number of compounding periods per year. In this case, it's going to be 12. If you're going to be charged interest monthly, you will be charged interest 12 times per year. So we can divide these two things out and we can get 1.6666666667%. And you want to go out as many decimal places as you possibly can, thereby giving you a more accurate answer at the end. The only number you want to round is the answer. Okay, so with this, we have the credit card company charging you a monthly interest rate of 1.6666666667%. All right, so how can you figure this out every single time? Well, we have to take R, the interest rate. We can divide it by M, which is the number of compoundings, and that will give us I, the interest rate per compounding period. So here are all of the variables defined in this equation. On this slide, I'm going to go over very quickly the nominal rate and how it is different from the effective rate. So nominal rates are not adjusted to show the full effect of compounding. And this stated rate, I'll get to that in a minute. Effective rates do adjust to show the full effect of compounding. So the real world example here is that my bank offers me a checking account with a rate of 2.1781%. Interest will be paid monthly in my checking account. What is the effective rate? So again, anytime you're given a rate, it will be nominal. It'll be for the entire year. And it's nominal because the interest will be paid to me monthly. To find the effective rate, what we will use is this formula here. Here we have the E, capital E, for effective rate, go figure. This will be 1 plus the interest rate per compounding, raise it to the number of compoundings in a year power minus 1. So let's figure all this stuff out. We have a 2.1781. This is happening monthly, so that'll mean divide by 12. And that'll give me this percentage here. But because we are about to put this percentage into a formula, we have to have it as a decimal. So here's the decimal equivalent. Move the decimal point 2 to the left to get the decimal equivalent. The number of compoundings here we know per year will be 12 because, again, this is happening monthly. So it looks like we have everything we need to fill everything in. So I can fill everything in as follows. So the I is here, the M is here, whoops. And again, you can just use a calculator to crunch this out. So here, when you put this in the calculator and do actually crunch it out, you'll get 0.021999755. But we are reporting back an interest rate, and this won't make a lot of sense to almost anyone until we put it into a percentage. So this will be 2.1999755, and then you can round. This is a percent. This would be about 2.2%. Now, the stated rate that I mentioned earlier, it depends on what you are getting interest for. If the bank is charging you interest, they probably want to show you the nominal interest rate, because the nominal interest rate, as you'll notice, is smaller, slightly smaller, but smaller nonetheless than the effective rate. So they want you to think, they want you to have a good peace of mind that you're getting a good rate. Whereas, and this is what my bank does, if the bank were to pay you money, like in a checking account, say, like my bank does, my bank actually lists the effective rate to make you think you're getting a better deal than any other bank. And this is common practice for all banks, but my bank definitely does display the 2.2%. And again, it's just that psychological thing to make you think you're getting a better interest rate. Let's take a look at the compound interest formula now. All right, here we go with compound interest. This is the formula that is given. So we have A and P being the future and present amounts. Those are pretty standard, pretty normal. I've already mentioned how I works a couple times this video already. I being R, the nominal interest rate, over M, the number of compoundings per year. So that is the rate per compounding period. And we have N. N is the number of total compoundings. I forgot to define T here. So there we go. We have the number of years times the number of compoundings per year. And generally this N can get really, really wacky, because what we can do is we can make the time frame that money is being invested some wacky number of years, like, 17 months or 37 quarters. And you would have to figure out how many years would be actually there, like we've done in the past. So very quickly here, the number of compoundings per year will have a chance to be any of these numbers, and I wanted to have a complete list. This 2 The number of compoundings per year being 2, semi-annual. That one I have not covered yet, but I think semi-annual makes pretty good sense there, that it would have to only happen twice a year. All right, so that being said, we start off with a relatively easy example down here. It says find the future amount if you know the rate per compounding period, the total number of compoundings, and the present value. So essentially all we're doing is we're taking these values here for I, N, and P, and we're just going to drop them right into this formula. So let's do that really quickly here. We can have A equals 15,210 times 1 plus 0.0319 raised to the 50th power. Now, of course, there could always be a trick here. If you're not careful, you could be given a percentage here that you would have to turn into a decimal. So just beware of what you're given. You always want to have a decimal when you're working in the formula. So from here, just plink this into a calculator. $73,115.56. So there is the answer for this first example. Now, if you think they're always going to be this easy, of course they're not always going to be this easy, because we could be giving you, instead of I right off the bat, we could be giving you a nominal interest rate as well as a number of compoundings per year, as well as a number of years, and then you've got to go through and figure out I and M yourself. Then, based upon whether you're given A or P, you may have to divide or not. Let's take a look at some more examples. All right, for this second equation, we're going to find the present value if the future value is 3 million. I think that's a great goal. The number of total compoundings is 480, and the interest rate per compounding is 0.83%. Ooh, percents. I don't like it. I want to move it right away. This is going to be 0.0083 as a decimal. So we want to use this in our formula. And yeah, let's just put these numbers in. So we can get our formula here. A equals P times 1 plus I raised to the n power. We can substitute all of the numbers in the correct place. So the 3 million will be equal to P times 1 plus, what is this? 0.0083 raised to the 480 power. So how would we do this? Well, the first thing you would want to do this time is you would want to simplify this portion first. And you would get 52.855. So let's just do this. 52.855. How many decimal places? 26453. 26453. There we go. So there's that, and here's our 3 million. So we have P times this number. All we have to do then is divide both sides by 52.855, blah, 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 blah. And we will get the answer for P. The present value needed here would be $56,758.77. Again, whenever you're figuring, solving for a money amount, you want to go out to 2 decimal places. Now, let's say you don't enjoy writing out 500,000 different decimal places. If you wanted to, and you could, it just makes the calculation a lot harder, I think. You could not even write out this step right here. You could just divide both sides. So from here, you could have gone divide both sides by 1 plus 0.0083 to the 480 power. and you would have been left with P right away. But then for some reason, students have issues typing this all in and getting an answer, which then probably requires them to type this bottom portion in first and get a bunch of decimal places and then round at the end. So however you want to do it, either crunch this number here, then divide, or divide and then crunch this number. It's up to you. You're going to get the same answer. All right, next example, find t. So here we go. This is our first example where we're not just going to be able to substitute into the compound interest formula. And you know that because we're trying to find some number of years. We're trying to find how long it'll take for an investment of $20,000 right now to grow into $750,000 much later at a nominal annual interest rate of 7.2% compounded monthly. So there's a lot to unpack here. The first of which being we need I, and so I will be 7.2% over 12, which is 0.6%, which is really 0.006 as a decimal, which is what we'll need for our formula. In our equation, as you can see up here, we have n. N is the total number of compoundings, which is the number of compoundings per year, which is 12 in this case because we have monthly. But it's also multiplied by the number of years, which we don't know. So what I'm going to do is I'm just going to leave this as n for right now in our formula. We'll deal with t when we get to n. We know A, we know P. So let's set this formula up here. So here's the formula set up for us nicely. As you can see back up here, A is $750,000. P is $20,000. 1 plus I, there it is. N, yep, there it is. And we have to leave N alone because N depends on T. And if we don't know T, then we can't know N. So the first thing that we will do here is we will divide, because we're trying to isolate n, we're going to try to get rid of everything we can here. So we're going to divide by 20,000, and that leaves us with a 37.5 equaling a 1.006 raised to the nth power. And yes, I can do this. I can add these two things together in here because they're both numbers. Now to bring back a prior topic that you should know coming into this video, logarithms. This is an exponential equation, and I can tell it's an exponential equation because the variable is in the exponent. If you want to solve for this variable, we have to use logarithms. That's the only way to get the variable out of the exponent. So we take the log of both sides. So I'm going to write it like this. We take the natural log of both sides. So 37.5 and 1.006 raised to the nth power. Yeah, we're allowed to do that. The next step is then we can use the power rule for logs to move any exponents we have to the front of a log. And yeah, you'll be able to use this process every single time. So that means we will have here the natural log of 37.5 equals n times the natural log of 1.006. All right. So lastly, if we're trying to solve for n here, all we have to do is then divide by natural log 1.006. Pretty simple. So now we have almost our final answer. We have n equals natural log of 37.5 divided by natural log of 1.006. And we can calculate that on a calculator to be 605.86718. Now, that's great. It feels good. We got an answer. Is it what we're looking for? Well, let's see here. We've done a lot of work. There's been a lot of talking. There's been a lot of writing. This is n equals all of this, but we're looking for the number of years. Oh, there's another step. Okay, so let's remember, n is the same thing as mt, where n is the number of compoundings per period. So we know n is 605 point decimal places, and m is 12. We used it way back here. So in this equation, if we're trying to solve for time, if we just take n and divide it by m, we will have isolated t. So if we divide 605 point a bunch of decimal places by 12, we will end up with 50.488 years, and then you can round as necessary. But that's how you're going to find the number of years every single time. Last example for compound interest here, more of a real-worldy feeling example. If you want $20,000, presumably for a down payment for a new car 5 years from now, how much do you need to invest at 1.75% interest compounded semi-annually? So you're basically trying to figure out how much money do you need right now, present day. We need to know a present value. So I know over here that this 20,000 would be A. Here is a T. So that's nice. That's the number of years is a T. Semi-annually tells me N will equal 2. Here we have the R, the nominal interest rate. Sorry, this N is not 2. This is M equals 2. But that's it. That's all the information we need in order to be successful. So if I write down the formula, it's A equals P times 1 plus I to the N power. It seems as though we've got some figuring to do. So I is R over M, and remember we need this to be a decimal, so it'll be 0.0175. The number of compoundings per year, if it's semi-annual, is 2. We can divide that out in a second. And N is M times T, or T times M. And this one I can do more readily in my head. M is 2, T is 5, that is 10. Let me get the number for the interest rate per compounding period. All right, here's the interest rate per compounding period, 0.00875. So now that we have figured out these numbers, we can just plink them right into the formula. So n will be 10, this will be 0.00875, p is p, we don't know p, we're looking for p, and a is 20,000. So here it is again. I substituted all of the numbers into the correct places. A is 20,000, I is this, N is this, as I just mentioned. Then if you want, you can just divide right away by anything that is not P to get this expression. And when you actually divide those two numbers together, you will get $18,331.35. And it doesn't seem awfully useful to be just putting down this big chunk of money and letting it sit without actually saving like a little bit extra per month over those 5 years. I bet there's some more math we can learn about that next video. All right, so that was compound interest. Let's look at continuously compounded interest. It's just a little bit different. So here is the continuously compounded interest formula. It is A equals P E raised to the RT power. So over here I have everything listed out. A is the future amount again, P is the present amount, R is the nominal rate, and yeah, we just get to use the nominal rate right in the formula, and T being the number of years. So again here, with the number of years, you might be thrown a curveball, and given a time and a number of weeks or in a number of months or in a number of half years or something like this. So just make sure that you are converting all time lengths into years. One thing you may have noticed is that I did not write down E over here anywhere. E is what we call the natural base, and E is always approximately 2.71. So E is very similar to pi, where pi is 3.14 as a decimal approximation. E is 2.71 as a decimal approximation, but E represents a number. That being said, you will never, ever, ever use 2.71 in any calculation. You will use E. Your calculator, even hopefully most likely the one on your phone, has an E button, and you'll see it'll be 2.71. So when we use the continuously compounded formula, you will have to use E. It will be exact in your calculator. It will be exact in your calculations. All right, that being said, the question often gets asked, when do I know I should use this formula, the continuously compounded formula, or the compounded formula, like I did in the past few slides? That's very simple. You will use the previous formula, A equals P times 1 plus I to the n power. You'll use that formula. If you don't see the words continuously compounded or compounded continuously, basically you don't see the word continuously in there, you won't use this one right here. If you do see the word continuously compounded, you will use this one right here. Pretty simple. All right, let's look at an example. Sorry about that. Before we even get into an example, I want to make it pretty clear that in finance, in the real world, the continuously compounded formula generally never gets used. This is one of those rare times you can use the word never and be right. Generally never gets used. What the continuously compounded interest formula is good for in most cases are applications outside of finance, like population tracking. Is it growing? Is it decaying? It's used for seismic activity when earthquakes happened. It's used to help string together frequencies of different notes that will sound good and explain music theory. It's good for a lot of things, but generally outside of the world of finance. All right, let's get to that first example. A credit card company is switching over to a continuous compounded model to charge interest. How much interest would be charged for a month if the balance is $1,536 and the rate is 17.99%? All right, so this question is asking how much interest would be charged. So in order to figure this out, we would still have to go through and find A. So let's do that first. Let's say here A equals, the present value is $1,536. We know it's continuously compounded. We know the interest rate is 0.1799 as a decimal. Again, here's a percentage rate. We have to move the decimal point 2 to the left to find the interest rate, the decimal interest rate. And the time here, time should be in years. And we're given 1 month. So the time here would be 1/12 of a year. Remember, it's the how many months was there divided by how many months there were in a year. Remember converting times over into years. Right. All right. So we have this, and look at this. We can just calculate all of this in a calculator to be $1,559.20. Okay, so this is what the balance would be at the end of the month. This does not answer the question how much interest would be charged for a month if the balance blah blah blah. How would we figure out what the interest would be? Well, in addition to finding the A, what we would have to do is we would have to also then subtract P from A. Right? The future amount minus the present amount is what gave us the interest for the entire period. So that is $1,559.20 minus $1,536, which gives us an interest amount of $23.20. So this is how much interest was charged over that 1 month period. I want to take a few minutes to discuss how to solve for R and T in the continuous compounding situation. This is very, very similar to what we looked at earlier with the compounding interest formula. So here we have this is the exponential piece, and if we don't know R or T, then the variable will be in the exponent. And in order to be successful in getting the variable out of the exponent, we will first have to do what we did over there in the previous example. We're always going to have to divide by P first. So there we go. That leaves us with A over P equals e to the RT power. Then we took the natural log of both sides to get something like this. We had the natural log of A over P equals, and then sort of simultaneously we moved the exponents to the front because that is a property of logs that we are allowed to use. So RT times the natural log of E. But what's really awesome about this continuously compounding situation is that the natural log of E is always going to end up being 1. So we don't need it there. So we are just left with this formula that natural log of A over P equals R times T. And so from this point, if we are trying to solve for R, then we can just divide by T. And if we're trying to solve for T, we can just divide by R. So it's a very similar process whether you're solving for R or T. So don't let the variables confuse you as you go through and try to do this. Let's take a look at a couple examples and we can be done with the video. Okay, so first example here, let's take a look at having a future amount of $2 million and a present amount of $10,000. And you were investing your $10,000 at 8% as a nominal interest rate. Again, we don't have to worry about the interest rate as a nominal or effective or interest rate per compounding period if we're dealing with a continuously compounded situation. So, and again, I want to say something about these numbers that I picked. These kind of represent some sort of retirement situation here. you probably can muster up $10,000 to save. And if you invested in the stock market in the correct things, whatever that means, you can probably earn 8% per year. And you want to have about $2 million when you retire, maybe more. I just picked 2 million. The last thing we're doing is we're trying to figure out how long that would take. So that being said, I'm just going to follow this process up here. We can divide by P. So I'm going to go ahead and do that. I'm going to divide by 10,000. So divide by 10,000. And I'll get, what would that end up being? All these reduce away. That leaves me with, what is that, 200? Okay. 200 equals e to the 0.08 t power. We can now take the natural log of both sides. So there's the natural log of both sides, and simultaneously we can bring this to the front of this natural log. So this will give me natural log of 200 equals 0.08 t. What is that? Natural log of e, which is just 1. So that really doesn't change the right side of our equation. To solve for t then, we can divide by 0.08 and get that t will equal natural log of 200 divided by 0.08. Now, if you're like me, that means absolutely nothing. And if you are working as an investor and you're trying to tell people that you can turn their $10,000 into $2 million in natural log of 200 over 0.008 years, they're going to look at you goofy. All right, so you can type all of this into, guess what, a calculator. And you can see that the time will end up being 66.22897. 22897 years for money to grow from $10,000 to $2 million. And then you'll have to decide whether or not that is worth it to you. Do you stop a little bit early and take a smaller amount of money? All that fun stuff. But really, this scenario doesn't make sense in the real world most of the time. Just having $10,000 and 66 years to wait doesn't make a whole lot of sense. Most people will put away the same amount of money every month into an IRA, into a savings account, into a pension. And that is what we would call an annuity, and I'll be coming back with a video on that very soon. Just to point out, this is the last example I'm doing for this video, but if you knew a time here, then the time would be a number and this would be R, but it's exactly the same solving process. I hope this video makes sense. I hope you understand what's going on. I hope this gives you a better insight into how compounding works. Good luck, everybody.